What have you been running around doing?
Just getting odds and ends organized for running the class I'm going to teach.
Oh, you're teaching class. What's it called?
Age of Mammals.
Ooh,
Yeah.
nice. I saw the Age of Dinosaurs
Yeah.
one, but I didn't know they had an Age of Mammals.
Yeah, it has kind of had a hiatus, I guess. So it wasn't taught for, I don't know, 3, 4, 5 years.
Yeah.
And so it's kind of fallen out of like the minds of pretty much everybody on campus. Yeah. So we're trying to bring it back, and Chris couldn't do it this semester, so I'm gonna do it for now, and then he's supposed to take it over and make it a regular thing. Because they're trying to kind of reboot both of those courses.
Is that a late Cretaceous to Holocene?
Yeah, essentially, yeah, it is, and it's so we talk about, right. We start in the Mesozoic and kind of move all the way up to the present, but more than that, it's kind of designed as just a science course and like a critical thinking course almost. So we spend a lot of time talking about how do we know what we know. Yeah. You know, you read something about mammals in the past, especially, or in the present. How do they know that? You know, so that's a big emphasis, is trying to get the students to wonder, what could that statement be based on? How could you get to that conclusion, right? Assess this statement, right? Critically. Mm-hmm. It's a good class in that sense.
I really appreciated that about Chris when he was my professor. And everybody that does paleontology here at the Jackson School, you guys are very in tune with the deep-rooted philosophic questions of research, and what are the different biases. And it was really cool to learn that in introductory geology. I don't know of other programs. I can't speak for other programs, but I haven't been in any other real classes that have a big emphasis on how do we know this? You know? How do we know what we know? What's the evidence behind this? What are the different biases?
Yep.
And that really stuck with me. I continue to think about that as I do
that's good.
stuff
That's
to
great.
this day. Yeah.
That's perfect. Yeah, I think that is a big bonus of the paleontology program at UT. And I think it comes from having really researchers here that came out of their PhD programs on top of the world, at the forefront of their field, and then have remained there for decades. And so that's where their headspace has to be. And that's one of the benefits of us going to school here, is we get that sort of training. And I think it's even more important now that the internet makes us feel like we all know everything. And if we don't, well, I can know it in 20 seconds. But it's really we're just consuming this information that's on our phone, right? That's coming up in a Google search. And I think it's really easy to just consume it and not think about it.
I agree.
And then what do you really know, right? You just read that, but where did that come from? How did they make that statement? What is it based on? Are you just repeating stuff that's nonsense?
Yeah.
Do you know the difference? Do you know how to tell the difference?
Yeah, well, I didn't know we'd talk about a little bit of politics on the paleontology podcast, but I feel like our education system in the U.S. at least is very, here's the fact, memorize it, and then repeat it to me, or make sure you, how it measures how well you can repeat and hold information, and not necessarily how well you can think about exactly what you were saying, the how and the why, and questioning everything. And so you're kind of trained to not only try to hold as much information as you can, but also repeat as much information as you can. And you always want to get it 100% correct, right?
Yep.
Because you have percentage scores, even through college.
You're
very much assessed on how well you're able to do on this test, or how well. And so and some of the undergrad research that I've done, there's no right answer to the problem. And that drove me insane.
Yeah.
It was like, how can we just say, I don't know? Like, you have to have an answer, right? And the answer has to be right. Like, this doesn't make any sense to me.
Yeah, I had a student like that this summer in the Geoforest program that I helped with, and he really had a hard time coming to the conclusion that we were going to finish this project and not have answered the question that we set out to answer. And he just couldn't square it. He was not okay with that. But that's where we were. That's the limits of the evidence that we had available to us. What else can we do? That is actually how science works. So, yeah, and I think you're right about what you're saying, the memorization, right? And I think that's especially true of like grade school and undergrad. And I think in the past it had to be like that to some extent because the student themselves had to become the source of information, right? Like that's where you're keeping those facts is in your brain. But now we don't. We keep it, it's on Google or whatever, right? It's just out there and we can retrieve it whenever we want. So that memorization doesn't really matter now, I don't think. Not nearly in the same way. I mean, you still have to know what tool you need and right what you're doing and stuff like that. But memorizing all these facts, they're available to us. We can download them in a second. It's more about what do we do with all this information? I think there's like this paradox that the more information that's out there and freely available and easily accessible on the internet, like the less we actually as individuals know about all of that information because we can just pluck it out, consume it, repeat it, discard, right? And there's no real thinking about it.
What do you think that's done for paleontology? Because there is a lot of like memorization or...
Yeah.
I feel like there's a lot of pattern recognition.
Yeah.
Like knowing what bones look like what or what bones are probably from what animals. And then... but there is also like a lot of memorization of like different species and things like that. Do you think that's like taken a load off of or that specific like kind of load on the researchers to like have all these things memorized? You think that's taken that off?
No, I don't. Maybe to some extent. I think people that are passionate about it, that are young, still do that. Like I meet these young people all the time. They can tell me every name of everything. They can talk about when it was found or who wrote about it, right? They're still memorizing this stuff because they like just love it. So how else can you not get it stored away in your brain permanently? But I think what it does do is it makes, because all of that information isn't only stored in the brains of experts, it is widely available if you dig around enough. And that gives a real advantage to people that aren't at the big school with the big museum or the big paleontologist, right? Or maybe outside of the United States or Western Europe, right? Where you just don't have all of the resources, the same amount of library, the same amount of expert knowledge getting conveyed to you. You can get it, right? So I think it really kind of evens out the playing field and makes it more possible to be a paleontologist like wherever you are, whatever circumstance you might come from.
Mm-hmm. Yeah, Trung is like that. He knows. I used to, like a year ago, we went through this park in Houston, and he calls it herping.
Yeah,
where you go out and like try to find reptiles, and he knew like the name and scientific name for everything.
Yep,
and he can find stuff everywhere, and it's just like it was just mind-boggling to me that he could do that. But him and really a lot of people at Jackson are in love with paleontology.
Yeah.
I remember, so I texted Janet before this, and I was like, hey, I'm interviewing John, and I was wondering if you had any questions. And she was like, oh, yes. And she was sending me paragraphs of stuff. And it's just like amazing how passionate people are about this niche field. And I feel like you Well, I guess I'll throw out, and you can confirm or deny that, like, to be a paleontologist, I feel like you kind of have to be really passionate about it because it is very niche. It seems like really hard work, and it's not like, I don't know, petroleum engineering where you're getting heavily compensated, so you can kind of you can justify all that hard work that you're doing with the amount of money you're getting. There's not as much in paleontology.
Yeah, I mean, I don't think about that as justification. I think it's just a more practical field. Paleontology is not a practical field, right? There's not really a role for us in most places in the world outside of academia. So that, right? Like, I think our knowledge is valuable. I think our knowledge is actually really broad based. We know about biology and geology and right chemistry, all of these. We know how the world functions and its history. It's really useful knowledge, but at the end of the day, the world doesn't need paleontologists to function on a day-to-day level. And so, yeah, it makes it difficult to find a job. The jobs are going to be low paying, hyper competitive. So that's what makes it all hard. Yeah, for sure. And kind of limits, right? I think it really constrains people and their choices. And a lot of people just, right, get to some level, maybe to undergrad, maybe sooner, maybe a little later, and realize this isn't going to work for like what I want out of life. Like this track, they're not the same thing. I got to do something else.
What made you decide to pursue paleontology despite those constraints? Did you know of those constraints beforehand?
Absolutely. Yeah. I mean, I was really, really well aware of them. It was really apparent to me. And that made me cautious. And so I always I adopted the mindset of I'm going to keep doing this as long as I can and just kind of feel lucky that I'm doing it while I am doing it, right? Because the idea of like going into debt to go to grad school for paleontology, no, I was not going to do that, right? And just all of those sort of constraints made me realize this is a lucky thing. It might be limited. I don't know. I'm going to keep doing what I can while I can, and we'll see how it goes. But I got into it because I like animals. I just like animals. I think they're so cool. And that's what if left to my own devices, that's what I end up thinking about. And so it's easy to be, right? If you're passionate about it, it's easy to just learn all those names and get way down these rabbit holes because it doesn't feel like work. It doesn't feel like effort. It's your own curiosity driving it.
Yeah. What did the path look like? Because I know that you weren't paleontology through your whole like undergrad to master's to PhD route. Like you kind of bounced around a little bit.
Yeah.
And it seems like your love of animals led you here, but why not like zoology or something different?
Yeah, that's good. I think as a kid, my uncle was a zookeeper. And so I was like, that's what I want to be. Like, give me a break. But my parents, he lived kind of close to us, and my parents were like, Saul makes no money. They're like, they didn't say it, but they implied that that's not a good job. And I don't know, I took that in and was like, oh, well, I can't do that. And I had like these little picture books of like prehistoric animals, those were my favorite books. But I also felt like for some reason I couldn't do that. Like I just didn't think people did that. You know what I mean? It's like it seemed like being an astronaut to me. Somebody does that, but like 5 people do that, Like that's not me. So I actually went to undergrad for business. And I didn't really go to school very much. And for some reason, I signed up for an archaeology field school the first summer of undergrad. And they took you out in the field and they taught you how to do archaeology. And I liked it. Like, I liked being outside. there's animals outside, right? And just as a kid, I was always outside, and I got to like find stuff. You get like just that discovery feeling. Really cool. So I changed my major. I just kind of fit better with those people too. I changed my major, and I graduated undergrad and started doing archaeology, getting jobs, being an archaeologist. And I liked it more or less, but then I would encounter, or the people that were my bosses usually were master's students or PhD students, or they'd just gotten their master's and were kind of taking a break and working before going back. And so they would talk about what they do. And I just would think to myself, like, I don't know how they are doing this, because that sounds really, really uninteresting to me. Yeah. Like, the choices of humans in the past in regards to what stone tools, materials they used, or what materials they made their ceramics with, or what were they doing around this fire pit. I just thought, I do not care. And like the analyses that they're working on to answer those questions, it's so much work, and I don't understand, like your taste must change as you get older and you get into this, because right now, like, I don't know, that tastes like soap to me. I don't want to eat it. And I ended up realizing after a while that no, I just am not interested in those past people. And it was animal bones coming out of sites that were drawing me down rabbit holes, that were grabbing my attention and my curiosity and leading me places intellectually that I didn't even think about, because it was just interesting and I was curious, right? It was just natural. And after a little bit of that, I realized, oh yeah, I'm not interested in people. I'm interested in animals. And I like kind of looking at them through the past and thinking about animals today in the context of where they came from. Why are they like that? Why are these things here and not those things? Mm-hmm. And so, yeah, that is generally what my path. It was kind of circuitous. Mm-hmm. So eventually, 10 years after my undergrad, I went back and got a master's, and then came here. But yeah, it was kind of that initial foray into archaeology got me into the past, and then also kind of taught me what I didn't like and showed me something I did, and led me back to animals and showed me, like, right, there was a way I could study animals. I could work with animals. That wasn't a zookeeper, right? That wasn't these other things. There was a possible path for me after all.
I mean, I found that things showing you what you don't like are probably just as, if not more important than you finding something that you actually like.
Yeah.
It really helps narrow the search. And also, I really, really respect paleontologists, because it's such a nice, it's such a perfect mesh of biology and ecology, but then also geology. Mm-hmm. And you have to have skill sets in both of those sciences. And it seems very interdisciplinary. And then the more high-tech analysis, like you guys are doing the CT scanning and things like that, you have to learn all of that science.
Yeah, right.
And with the Homotherium tooth, the guy who had it was a U.S. representative, right?
Right, yeah.
Yeah, that was pretty cool. But he was also trained in dentistry, which is why he knew that it probably was a tooth.
Yeah, that's right.
And I think just things like that are amazing, how you can take all of these fields of science and mesh them together and come up with answers that to me are amazing. I don't even know what animals did millions of years ago. It's absolutely wild.
Yeah, it's exciting.
Yeah.
Yeah.
And then also, I think there is a lot of value in paleontology, like with the Texas Rails paper that you wrote. That seemed like a really good way to constrain climate change through time, right? If the birds are following, or not even the birds, but I think you mentioned muskrats and lemmings. They're going to follow the habitats, and the habitats change due to climate change, and you can really get a good, especially when you can age date the bones pretty well, you can get a good constraint on, when were things here very marshy, or when were they colder, or whatever.
I think that's the greatest value of these bones, right? The things sitting behind us, the things that I write about, they're our textbook of Earth history. Part of it, right? Not the whole book, but they're a big part of that history record, and they let us look at the past. They let us look at those environments and the climate, and without them, I think our view of the world would be so narrow, right? Our time only really knowing what we exist in and with.
That'd be very, that's how humans did.
Oh yeah.
Survive for,
right.
Paleontology is a very young science, compared to like physics or, other forms of science. Science in general, like the scientific method's pretty young.
Yeah, pretty young.
So yeah, it's, that's such a cool conversation topic too. How these churches in Europe or whatever would find huge like remnants of predatory whales, and they thought they were dragons or demons or so, and you would try to explain it with the tools that you had, and you didn't have the scientific method at the time to be able to discern what this might be. So you kind of try to find the explanation that you can, and
they're just kind of grasping at straws, right? What else can they do? And that that's satisfactory in that moment. You get some kind of answer that makes sense to you about whatever this is. And I think that was sufficient for most of human history. But I think at this point, as we really dominate the planet and its ecosystems, and we become so numerous as individuals, but still dependent on these natural systems of the planet to survive, that it's really not sufficient anymore. Those sorts of old ad hoc answers to these natural history questions, we really need to know. We need a guide for how the planet works before we alter it in a way that undermines our own ability to be happy and healthy.
Yeah. Kind of, I think generally on the topic, I did want to ask you, you seem kind of like an atypical grad student. Like I haven't seen a grad student who has as much media coverage. You were on the cover of the Jackson School magazine.
Yeah.
And the cave stuff is super novel and it's so cool. So I can definitely understand why. But I'm curious if like that amount of media coverage has changed your grad student experience or kind of like the research that you do.
I don't think it's changed it. I think in part it's developed as a result of what I've been able to do here, and what I've been able to do in terms of research and where I can do that research and that publicity are both products of this place. I think being at another university or even a different department at this university, I wouldn't have the same opportunities for access to fieldwork and for this publicity, right? Because I started thinking about promoting myself in that way after talking to other paleontologists that we were having come visit for the paleontology seminar in the department. And one of them in particular said, you should be writing press releases. You should be doing all of this stuff. Anytime you do anything, you can't just let it like go out there and expect it to get attention. Like you have to develop the attention. You have to put out some prompt that says, hey, I'm doing this cool thing. And near the same time, Chris Bell had just published this paper about a manatee fossil from Texas, from the same beach, actually, that Homotherium fossil came from.
Yeah, over near kind of Texas-Louisiana border.
Right.
Yeah.
Yeah. And And I was in his office one day, and like this PR team comes downstairs to meet with him to develop a story about these manatee fossils. And so I was cued into like, this department has people devoted to promoting us. And this other person is telling me I have to promote myself. And so I just asked Chris, like, who are these people? Like, how do you get them to promote you? And it turns out you just ask. And it helps if you have something interesting, right? Something appealing. But I have something appealing because I'm a student at UT in the Jackson School of Geosciences, right? Because that has afforded me certain opportunities in terms of field work to do interesting stuff in interesting places and have interesting pictures of it. And that all then, right? Then I go ask the PR people who are, right? I have that opportunity because of the department too. And they say, yeah, that's really cool. Cats in a cave and you have neat photos. Yeah, this is easy. Give us the content and we'll write a story. So I feel really lucky, right? I don't think any of that is common everywhere. I think I'm really lucky to have this.
Yeah. And I don't want to sell the audience short of just how cool the stuff you do is. Like the cave, like the wet caving and the spelunking and all this stuff, and the fact that you can like crawl down there all the way to like a mile underground and find bones is just so cool. It's so cool. It's some of the coolest field work I've ever seen.
It's great.
Yeah.
Yeah. Thank you. I mean, I love it. And again, I think it's another circumstance that I didn't expect, but I found here in Austin. This time, it's a lot of that field work, or me being able to do that field work, right? Because not everybody should try to do that field work. You can get hurt. This is technical.
The price for the coolness factor of it.
Yeah, right? You need some kind of training and technical skills to navigate some of these places. And not, right? Believe it or not, you can't just find people to help you develop those skills just anywhere. But it turns out because of all of the caves in this region on the Edwards Plateau of Central Texas and the proximity of this region to similar cave-rich regions in Mexico, Austin has, since the 50s, been like a caving hotspot. And people move here from all over North America to be part of this caving club here in Austin. And a lot of the fossils in this building were collected with their help, right? They are out in caves and they're finding bones and coming here and telling paleontologists, hey, we found this stuff. We can take you there. We can bring you stuff. We can train you. And that, again, is just kind of an opportunity that, I don't know, I was lucky to tap into. And then they started taking me places and showing me things and teaching me how to maneuver.
Yeah, that's a great topic of conversation that I wanted to cover as well, because we kind of defined your path from business to archaeology to paleontology, right? But how did you go from paleontology to like cave paleontology?
Oh, sure. Yeah. Well, I guess as a paleontologist, I'm a vertebrate paleontologist. So I'm interested in animals with bones, right? A backbone, mammals and fish and birds and reptiles and amphibians. And really, I'm interested in all of them because I want to know not just about saber-toothed cats or mammoths. I want to know, how do animal communities change over time? Why do they change?
It's like paleoecology, kind of.
Kind of, yeah. I mean, almost more just natural history. Like, why are there raccoons and rock squirrels and cottontail rabbits and roadrunners outside right now in this region and not some other set of animals, right? Think of another set of animals, extinct or not. Why don't we have those? How did this happen? And so I want to know, right? When did communities change in the past? How rapidly did they change? What is driving that change? When did those changes happen? When were those important events in history that if we remove them, we have a different present, right? And And so I started out on the Great Plains, and there's loads of fossils.
So that's like Texas Panhandle kind of area?
Yeah, exactly. Yeah. There's loads of fossils, and especially lots of fossils from the past 2.5 million years, the Quaternary. We're still in the Quaternary now, so it's really relevant to, right? It's part of the chapter of Earth history that we're still in. So if we go back to the beginning of that chapter, right, maybe we can read through the natural history record that's preserved and get to the present. And on the Great Plains, you can do that, but the fossils there are out on the surface. They accumulated in the past mostly in places with water. So lakes, lake beds, and river valleys. That's where stuff could accumulate, right? There are depressions on the landscape, so stuff can pile up in there and get buried and get preserved.
Water wants to wash things down there and things like that.
Right, and the water kind of concentrates the bones of many different animals from around an area that are all living together as part of one community and kind of collects them together and buries them, and maybe they stay buried, right?
Yeah, that would be it's like a little refrigerator down there.
Yeah.
Right?
Yeah,
it's
right.
cooler too.
Right.
Yeah.
And if we have this sort of Goldilocks series of events where everything just so happens, those bones can still be there for us to come and find and read about natural history. But in this part of Texas, I don't know, I have a house in South Austin, and I can't really dig a hole in my backyard, right? I garden a lot, and the soil is like this.
Pretty hard to get through that limestone.
Yeah, right? There's like sediment and then hundreds of feet of limestone. There are not a lot of places for sediment, let alone fossils, to accumulate on the surface. The surface has actually been shedding itself down to that top of that limestone bedrock for like 13,000 years. It's all been sloughing off of the top of this plateau.
Which is why we have like these huge hills in Austin, right? Or that's
in
more
part,
erosion of the
it's
limestone
more erosion.
itself.
Yeah. That's older erosion even.
Yeah.
But in this part of Texas, the fossils that I want to see, the fossils from the Quaternary, are in caves, because that is the same thing. It's kind of this depression. It's this open space where material can naturally accumulate, be concentrated, and be preserved. And it's actually a really good preservational environment, right? Because rather than it being kind of buried in an open air setting, it's actually underground. It's actually in like a room, right? That is its own sort of different temperature and moisture levels than on the surface. So fossils that I want to see in this part of Texas are in caves. And I knew that coming here. And that's where I was going to want to go if I did field work here. And I like doing field work.
So you were seeking out the caving.
I wasn't really seeking it out. I was seeking out interesting problems, interesting projects, right? And that was just natural. That's where the interesting stuff is going to be. So then it becomes, well, what cave? Like which of these has the materials that can let me find out something interesting?
Yeah.
Yeah.
I really like the analogy you used. I watched this new segment that you did. I have no idea how long ago it was. I couldn't tell you. It might have been super long ago. It might have been pretty recent. But you said a cave was like I said earlier, like a refrigerator. Basically, it's very cold. It's I don't know what the moisture would do to fossilization. Maybe you could comment on that. But very cold, dark. Not a lot coming in, not a lot coming out.
Yeah.
And but when you have something on the surface, it's like instead of leaving it in a refrigerator, you're leaving your sandwich on the countertop.
Yeah, right? I remember this.
It's gonna go bad a lot quicker.
Yeah, right. Yeah. It is. Mm-hmm. And there's more processes, natural processes that are going to break those natural materials down. Right? All kinds of things happen to an animal after they die. Yeah. And most of that happens pretty quickly, and all that soft, right? It's all really gross. All that soft tissue, all this moisture and other materials that make up our body gets destroyed pretty quick. A lot of it gets consumed by other organisms, and that's the really gross part. But even the bones are fairly easily destroyed in most situations. They dry out, they bake, they desiccate, they freeze, they thaw, they get crushed on, they get chewed on, right? You get plants growing in them and mining them kind of for materials for their own bodies. And even after they get buried on the surface, a lot of those processes could still occur. And especially on the surface, there's this problem of even preservation and destruction at another scale, right? So we could have the bone preserved, but everything in it may be destroyed. And everything in it, I mean proteins, like collagen and DNA. We need collagen to get good, reliable radiocarbon dates from bone. And DNA, wow, it's invaluable. It can tell us so much more than just the simple reading of the bones can. But on the surface, in most places, especially in the Great Plains, right, which we're in, even here in central Texas, there's pretty drastic temperature and moisture fluctuations, right? It's like, what is it? That's like 109 today or something. It's really hot. And in other parts of the year, it's much cooler than that. Sometimes, right, it's freakishly, we've had these cold snaps in the past 5-6 years in February, a couple times where we have really extreme cold. And then we have extreme variation in temperature or in moisture too, right? We can have huge thunderstorms. We can even have flooding in this part of the state really bad. And other times where my backyard has desiccation cracks like 2-3 inches wide and I can't find the bottom of them, right? And that variation in temperature and moisture destroys the biomolecules, the proteins and the ancient DNA in these bones. So even if the actual thing isn't destroyed, a lot of information has been lost. So we may have a book, but we can't read anything in it, right? We just know we have a book. This is what it looked like. But in caves, there's a lot of those processes of those agents of destruction aren't operating. For one, it's closed off to a lot of things. And two, they're really simple ecosystems in a lot of cases. There's not nearly the number of organisms, especially microbes and fungi and things like that are going to consume bones and destroy them. And because they're these closed underground places, they're really insulated. So most caves in central Texas are about 72 degrees year round. They're about 98% humidity. And it's always like that. And so if you store something away in there, right, it's like putting it in the wine cellar. It's a lot more stable just because it's out of the light, it's out of the rain, it's away from other animals, right? All of these things that are happening on the surface that are not happening in the caves, or at least happening much slower. So in caves, we're more likely to get good preservation of the physical part of the bone, but also then we have a really good chance to have the collagen we need for dates and even ancient DNA.
How does the mineralization of bones work in caves? Different than because you could definitely speak about this a lot better than I can, but I know that fossilization is where you have calcium bone from, let's say, a T-Rex 65 million years ago. 66 now, I think.
Yeah.
66 million years ago, T-Rex dies, and then the bone gets buried really quickly. And then over time, that bone mineralizes and becomes maybe not the rock that's around it, but it becomes rock, right? It's no longer like bone like we have in our body. How does that work in caves differently too?
Yeah, it's happening still, right? Because what's happening is that the materials that the animal put into that bone to construct that object, that skeletal element, are just not that stable, right? Relative to other materials. And so they're being destroyed. The bone itself is being destroyed over time. It's just degrading. The structures that hold it together are coming apart, right? Like at a molecular level, it's not super stable stuff. And so it's breaking down into carbon. But if you get the right circumstances, especially with the help of some water, you could have other more stable materials penetrating into that object and taking up the space that the original materials held. So you kind of have a replacement. This stuff is being destroyed, and we can put this stuff in its place. So you end up preserving the shape and in some cases, fine structures, details, but it's not the original thing anymore. It's been kind of converted. And the same thing's happening in a cave, but that in the cave, it's happening slower because it's just a more conducive environment, a more friendly environment, less destructive. So that bone is still being destroyed. It's being destroyed slower in a cave. So we're more likely to have more of the original content, right? Hence, in part, the greater likelihood of collagen and ancient DNA. We have more of the original stuff left, including biomolecules. But in caves, there's a real trick because a lot of caves are decorated, especially in this part of the state. They have stalactites hanging from the ceiling and stalagmites growing up from the floor. They have other structures and formations that are made from the same material, calcite, that's forming in the cave. And that stuff those cave formations are growing because water is moving through the bedrock and transporting minerals into the cave. And when it reaches the cave environment, this open setting, it mineralizes. It makes these mineral structures, right? Kind of like hard water formations on your tap, right? It's happening because that what's in the water. And so the water is coming into the cave and moving around in it, and it's mineral rich and just looking for some surface to kind of deposit some of the minerals that's carrying on. And so in a cave, you can have really relatively young bones, Pleistocene bones, that are really inorganic because they have absorbed so much calcite. Because the cave is such a calcite-rich, a mineral-rich environment, and there's so much mineral-rich hard water that you can actually get bones becoming really, really fossilized, really pretty quickly in terms of geologic time, in a way that really doesn't happen on the surface. So and that's not good for, right, trying to get biomolecules. All this water is flowing through that bone, and the original stuff is getting rinsed out, and it's just getting filled with calcite, just hard water deposit sort of structures. So there's kind of a good and a bad side about fossils in caves. It's not always working in our favor.
Yeah. That is really interesting, though, that you're studying a point in time, I guess, just like brushing aside the richness of minerals and the rapid rate at which bones mineralize. You're studying like this, in the grand scheme of life on Earth, like this small portion in time that's closest to us.
Right.
And so any degradation of biomolecules that you get is going to be, I guess, depending on the environment in the cave, usually less than things millions and millions of years
absolutely.
ago. And so there's this whole like I don't know the right word, but like paleogenealogy that goes with it. That's such an interesting field. What's done with that DNA whenever it's collected?
Yeah, I think working in the Quaternary allows us to do things that other paleontologists just can't. They just don't have the same materials available to them. And even even now, getting ancient DNA out of these bones from Central Texas caves is still, it's pretty extraordinary. I mean, 5-10 years ago, the consensus was it wasn't possible. The caves were too variable in temperature. They were too warm. This is not a good place to get ancient DNA, right? Little broken fossilized DNA fragments fossilized. But technology is advanced, our understanding has changed, and we know now it's possible. And so we can get ancient DNA out of Pleistocene Ice Age bones from caves in Central Texas, and it's huge because these fossils can tell us about who they are, who this animal was, right? In terms of what is its ancestry, who is it related to? And it can tell us that based on its shape, right? Like most of my siblings and most of my cousins have a nose like this. And so does my grandpa, right? And you can use that similarity to infer some things about who we're related to. And the same thing with his teeth and the shape of his skull and things like that. But we would learn a lot more about who I'm related to and who my cousins are related to if we could look at my entire genetic code, right? There's all sorts of little clues and pieces of evidence in there.
It's what the 23andMe kind of like ancestry.
Right? It can tell me so much more than just like, oh yeah, that's your grandpa. You guys have the same nose, right? And somebody else might have this nose and they may not be closely related to me at all, right? So they can present, it can be limited in the amount of information it can tell us, just a fossil. And it can be misleading too, because we may see similarities, right? Our primate pattern-seeking brain may see similarities that aren't really meaningful. We can find patterns even when there aren't any.
But, or you could have two species evolving similar.
Exactly.
What's the word?
We can have similar structures arise
yeah.
Out of some sort of ecological need or opportunity, not necessarily being present in two organisms because they share the same ancestor. Yeah. But the genetic code can really clarify a lot of those problems with it for us, right? There's a lot more there that can tell us about who these animals are, where they came from. And if we can tap into that, it's just a treasure trove of information. So we have to get it out of there. So we have to take some piece of bone and destroy it and get rid of like the actual bone stuff, this inorganic mineral structure, and then try to isolate itty bitty teeny tiny fragments of DNA, right? We're working with like drops of clear fluid in little vials. And then we need to do certain things to these little DNA fragments. That's what ancient DNA is defined as, is broken short fragments of this long double helix structure, right? We just have little bits and pieces of it. So we have like corners of pages from a book. Mm-hmm. And we need to reconstruct that book. So we have to prepare those little bits and pieces in a certain way so that they make copies of themselves. So we have a lot of them. So we have a lot of material we can study. And then we need to actually tell that code to start filling out the parts of itself that are no longer there based on what's present. And all of that takes a lot of time and energy and money. But if we're successful, then we've built back some of those pages, and we can kind of start to read who this organism is, who is it related to, what is this thing really? And yeah, there's nothing like it. That is the most reliable, most information rich piece of data that we can get.
I have to ask you, what do you think of them trying to resurrect mammoths and other Pleistocene megafauna?
I think it's mainly an intellectual and technology exercise. It's a showpiece to develop technologies that are practical and useful, right? So it's kind of like having, some like a concept car. Ford's never really going to make that thing, right? It's never really going to be available. It's a way to think about and to test new technologies. And I think that's what this Mammoth stuff is too. And if it isn't, then I think it's really problematic. I think, right, we can never really make a mammoth because any creature that comes out of this has to be born, right? It's a mammal. It has to be born. We can't just grow it in a petri dish. And so then what is it born from? Is born from like an Asian elephant, which is the closest living thing to a mammoth. But that's not a mammoth. And if we put something that's purely mammoth into that Asian elephant, its body is going to say, this is some foreign substance. It is not an Asian elephant material. I should attack it. Yeah. Right? It won't be viable. The body will not make that into a baby. So you have to kind of modify it and change it. And you're starting right from bits and pieces of a mammoth genome in the first place. So you're making something that is neither really mammoth nor Asian elephant. And then secondarily, even if you could make a mammoth that's like truly mammoth, where do we put it? What do we do with this thing?
I think the idea was Siberia.
Right. Yeah. And that is a place that mammoths used to live. They don't live there today. And there's good reasons for why they don't live there today. The habitat 13, 14,000 years ago that those animals lived in is not there. And as the climate changes and, right, the Siberia changes, it becomes something closer, but it's still not the same thing, and it will never be the same thing. It cannot be. So you have this animal that you've made and spent a lot of money on, but it's actually a living, breathing thing. It's not a robot. It's not a toy. It's not animatronic, right? And so they just like the philosophical, the ethical issues here, I think are outrageous.
Yeah, and elephants are very intelligent and emotionally intelligent creatures too, so I'd imagine mammoths are as well.
Right. And so do you make this thing that has no real place to live? And why would you put it out in the wild anyway? This is like some $1 billion animal. Like, no, we're keeping this thing in the clean room. Is like, what? Why? How are you going to keep it alive for 60 years? And if you did put it outside in the wild, like what? That is almost just as bad, right? You're kind of creating this thing that has no place on the planet today. Doesn't have kin. Right? It's just this like
this social animal that's a mixture of. It's not even really what it's supposed to be because you have to mix some Asian elephant into it. That you're right has no habitat close to what it had, 20,000 years ago, and
what would you do with it?
Yeah,
everybody comes looks at it. Nobody comes looks at it.
It's like elephants in the zoo. Like they always look so depressed and lonely,
and at least that has some utility, right? And I guess you could argue you could use a mammoth also for education in a similar way, right? Maybe you inspire some new people to get engaged in paleontology or conservation or something by showing them this mammoth. But I think you're creating more problems than you are anything good. And ultimately, I just think about the money involved. I don't think they're really ever going to get to these problems. I think they're using this as a concept car sort of issue, and to develop technology, to do things, attention, right? Money, excitement, interest, that can, right, all lead towards some real meaningful genetic technology breakthroughs, and maybe not ever make mammoth.
Yeah, I could see that. I think another idea they had was to try to resurrect the Tasmanian tiger, which is a lot more practical. And since it went extinct, less than 100 years ago.
Right? Yeah. Yeah, it's actually just about 100 now that the last individuals died in a zoo. And I think there we get a little bit closer towards something meaningful. In part because we know that animal went extinct because of our own actions. And that the animal community of Australia is less is diminished as a result of the loss of that predator. But again, what is this thing, right? Who is going to give birth to this animal, this first one, right? Some Tasmanian devil? Every other living marsupial carnivore is so different from that animal that I don't know. I don't know.
You get this.
What are you really making?
Yeah. For anyone that has pugs, I apologize in advance, but this pug-like monstrosity, I think what we've done to dogs in some breeds is pretty bad.
It's not healthy, right?
Yeah.
And I think we do things like that with animals. We kind of change their shape to suit our needs, and in many cases create these animals that are just not genetically or physically healthy. And in other cases, we put animals in places for reasons that we think initially are going to be useful, right? We accidentally bring rats to some island. Well, why don't we just bring some mongoose to that island too? They'll eat all these rats. And in almost every case, those experiments do not go the way we think they're going to, and we create more problems, right? And so these cloning projects are kind of like that to me, right? You're modifying this animal from what it should be, right? We're manipulating it in form and in other ways. And then what are we going to do with it? We're going to put it into some habitats in Australia? Is it actually going to behave like the extinct thing that we're trying to resurrect? Would we know? Or are we just putting mongoose on some other island, right? Some like human manufactured mongoose, right? Are we creating a situation like that? And I don't know how we can actually reassure ourselves that we're not making more harm than good in those sorts of experiments. They freak me out.
Yeah.
All that stuff.
So you're definitely on the more Dr. Grant spectrum in this Jurassic Park scenario. Definitely not the John Hammond.
No. I see way more problems than benefits.
I think this is going to be all conjecture because I haven't seen any actual scientific literature to back this up, but I think the argument of the company that was trying to resurrect the mammoths was that we played a part in their extinction from hunting them.
Yeah.
And I'm sure climate change played a part as well. But due to the absence of mammoths in Siberia, it changed from this big wide open grassland to this huge taiga forest, right? And so I think their argument is that if they release these mammoths into Siberia, then they'll act like Asian elephants in India and kind of knock down trees, make room for those grasses to grow, kind of almost cultivate the forest in a way. But I'm not entirely sure how robust of a plan that is and how much evidence there is to actually back that up.
Yeah, that's a big topic. And it's all kind of in the realm of conservation biology to some extent and is often talked about as rewilding. And this idea that that whether these animals went extinct during the Pleistocene or at some other time, they played some ecological role that when they're pulled out of that system, the system is changed, right? So we pull wolves out of Yellowstone and the ecosystem changes. And if we put them back, it changes too, And so as we've clearly modified natural ecosystems all over the planet in the past 20 to 14,000 years, especially on more recent end. So there is this idea that if we could put some animals in some places to not necessarily replace things that went extinct in terms of now we have a mammoth again, or now we have a thylacine again in Australia, but we have something performing the same ecological function as the thing that was lost. So yeah, this is not the same thing at all, right? But it's acting in a similar way. It's playing a similar role that can restore some of the other lost functionality of that system. And especially in places like Siberia, where as the permafrost melts, there's a lot of changes, including loss of carbon sequestration, right? This carbon is all these things are decomposing and changing carbon balance to some
methane
extent.
too, which is even nastier.
Right. Yeah. And if we could actually put some animals there that could help turn this place back into a grassland, we could help negate some of those negative changes, right? That probably are occurring as the result of human behaviors, right? Some anthropogenic climate change. Maybe we can mediate that by putting some animals with the appropriate ecological roles in some places where they're needed. So there's a guy, Harry Green, in biology here at UT. He's a fascinating guy. If you haven't heard about Harry Green with an E at the end, you should look him up. A really great scientist, really innovative, smart guy. But he is a big proponent of this rewilding effort. He would encourage Mustangs, wild horses in the American West. He would encourage the idea of moving things like tortoises, even Asian elephants and other animals into places that used to have this megafauna as a way to not put back what's been lost in terms of species, but to add back some of that functionality that's coming apart, right? As especially we remove a lot of the big animals from ecosystems, and especially a lot of the predators.
Yeah, because we lost horses in North America until like the Spanish brought them back, right?
Right. Yeah. They started out here 55 million years ago. Horses start out in North America. Like that's one of our continent's claim to fame, right? We had horses first, and they spend the next 55 million years here, pretty much until 10,000 years ago, and then that's it. Yeah. And the Spanish, right, unwittingly bring some back to their ancestral homeland.
So I guess to circle back to mammoths before we move on to another topic of conversation, I was curious because I've always been a little bit confused. How much of the extinction of mammoths is anthropogenic, like from humans? How much of human hunting, or I guess, is there like scientific evidence that human hunting played a large role in the reason why we don't have mammoths today?
Yeah, that's a great question. We have been debating that for, 60, 70, 80 years. And I don't think we have a good answer.
That's like a large chunk of paleontology's lifespan as a science.
Yeah. So, first of all, we had a really contentious debate in North America of whether humans were even here with those animals, ground sloths, saber-toothed cats, mammoths. Were we here or not? And eventually we're able to demonstrate, yeah, we were here. And we were here, and we actually killed some of these things too, right? So there are sites across North America, 18 or so, a dozen and a half, something like that, with mammoths that are clearly, or mastodons that are clearly butchered by humans. Our tools are there. Our cut marks are on the bone. Bones are modified in some cases. It's a crime scene. And there's a few other animals too that occur in the paleontological record, the archaeological record, as prey of Pleistocene humans. But that's it. And more than a few species went extinct at the end of the Pleistocene. And rapidly too, it seems. Within maybe 1,000 years or less. And it started out in the 60s is that extinction, as we started to be able to radiocarbon date things, looked like it occurred right at the same time as humans coming into North America. And our radiocarbon dates on human occurrence in North America were all like simultaneous almost, right? It seems like we entered the continent through Beringia, across this Bering Land Bridge from Asia into Alaska, and we quickly spread south and east and west, right, in every direction. Covered the continent down through Central America and into South America in a geologic instant. And that all those dates coincided with a lot of these terminal dates, these youngest dates on extinct animals, saber-toothed cats, ground sloths, mammoths. So this hypothesis was formed that these animals didn't know humans, they were naive. These humans were actually very good, had a technology very well suited for killing big game efficiently. And that's kind of the lifestyle of these people. And so there's this hypothesis. They spread quickly across the continent, encountering these animals that had never seen humans before, very trained hunters, very naive animals, and we just kind of went around wiping everything out, right? These are big animals. They reproduce slowly. Humans could have quickly a big impact. But at the same time, the climate is changing too. So there's forms these two camps that's saying, no, there's more changes than just the big animals going extinct. Bog lemmings moved out of Texas and most of Western North America. Humans didn't go around bopping every bog lemming, right? These little mice things on the head. There's something bigger going on, and it's climate. Climate is driving this. And so we've been kind of locked in that debate, in part because it's really hard to find that smoking gun. And to address this question, we need to be able to demonstrate relationships in time. So we need more than just the fossils of big animals. We need the fossils of the whole animal community. And we need to place those fossils in time. And really, we need some kind of chronology where we can observe a large amount of time so we can see, like, what is the baseline for this community? What is normal change in North America like? And how does that progress forward up until this dramatic conclusion? And most of the time, we don't have the whole animal community. We don't have dates because we don't have collagen. And we don't have this long view of natural history. We have little time slices. And it's often right around this dramatic event. It's really hard to see back beyond it. And so you think about coming into like a TV sitcom, and all I can really watch is the season finale. And I'm supposed to reconstruct why all that stuff is happening, right? And it's really complicated. This is like the end of Lost or something, and all I've seen is the last episode. I have no idea, right? I can make interpretations. I can infer things. I can use what I have available to me to understand why this happened. But it's always going to be kind of off. And it's just a big challenge to assemble that database of knowledge from the past to be able to get to this question. And it's a big problem for the Pleistocene because it's close in time, because it's us, because we can radiocarbon date things, and we have this kind of closer access, this more precise view of things, more precise way to measure things. So it comes down to, 1,000 years of error bar can make a huge difference on your date. Whereas if I'm studying, right, even Pliocene extinctions, 1,000 years is great. right? That's an instant. But 1,000 years really matter. And so the resolution that we need to achieve in our fossil record or in our natural history record to understand what is actually driving these changes in the community needs to be really high. We need really high resolution. And that it's just dang hard. And so we still debate it. We debate it a lot. And it's really hard to ascribe every change that happens in the animal community to either potential driver, climate or humans. And now we know more too. So we know that humans were actually here far earlier than the extinctions, and we're living with these animals for thousands of years, maybe tens of thousands of years before the extinction happened. But also, these animals experienced climate change before too. These same species experienced episodes of climate change earlier in the Pleistocene as glaciers waxed and waned across the northern hemisphere. So it's not as simple as that debate framed it in the 1960s. It's not just human overkill. It's not just climate. There's a lot more going on, and it's really difficult to discern that sort of nuance in the geologic record. And it for us as paleontologists, it becomes this little incremental thing where everybody's kind of adding a little bit over time. Each paleontologist working across the globe today, and each generation, we're adding a little bit. But it's a generational problem. I mean, I don't think we'll figure it out quickly and easily.
Yeah. I mean, it's definitely not a black and white thing. Like, I bet you there's climate change and human impacts. But what you mentioned at the end, where we had been around these animals for thousands of years, makes me think a little bit. And also, so 20,000 years ago at the last glacial maximum, there was that Laurentide ice sheet. For anybody listening, Laurentide ice sheet was this absolutely massive ice sheet that covered all of Canada and connected to Greenland and a lot of Alaska too, and a lot of the Canadian Rockies. And it went all the way down into about like Manhattan, kind of like covered the Great Lakes. Great Lakes are formed from the Laurentide. And that was the biggest ice sheet that we know of so far, besides like Snowball Earth. Like, that's like the biggest ice sheet that we have evidence for ever. And so last glacial maximum was particularly cold. So there might be, at least like my glaciological intuition would say that there's probably a little bit more intensity in climate change. But then, and there was like a thermal maximum in the interglacial before that.
Right. The climate of the planet, especially in the northern hemisphere, is shifting throughout the Pleistocene. It's not just glacial ice all the time, everywhere. The glaciers expand and they contract. And so we have glacial intervals when they're at their maximum. And then when they're at their minimum, we have these interglacial intervals. They're warmer and the glacials are colder. And it means different things to different animals. For some, they're gonna be able to expand their range in interglacial intervals, whereas others really shrink back and they have to leave certain places during interglacials, and vice versa. So these animals, these very same species, experience that climate change repeatedly throughout the Pleistocene. They experienced humans. But that's what I think makes the Pleistocene in part so interesting. A lot of the animals that live around us today were alive with these mammoths and saber-toothed cats and ground sloths, right? We were us. We were us. Just like you and me, we had the same mental capacity and physical capacity as you and I. So it's this familiar world, but it's also not. It's a different climate, different landscapes, and clearly a lot of different animals. And yet we can see familiar problems, right? We can see a human population that's spreading across the world, becoming more and more widespread and more numerous, and having more impact on everything around it. We could see a climate that's changing rapidly, and it's actually warming, right? At the end of the Pleistocene, part of what's happening is it goes into a warmer interval. Some people think of the present day as an interglacial relative to this last glacial episode. So we have humans spreading, becoming more impactful. We have a warming climate, and we have major changes in global ecosystems. So there are lessons there from this past that are really relevant to the present day. And if we can figure out what happened in the past, it's not an exact roadmap for what's going to happen next year or 1,000 years, 10,000 years into the future, but it certainly frames our understanding and helps us think about what could happen. It helps us understand how the Earth works. And if we push this button, what comes out? What do we get? Because we're pushing a lot of buttons now. There's a lot going on. And if we could frame our understanding better, we could do that with the past. If we could do that, then I think we're in a better position to be good Earthlings, right? Good humans. Yeah. We can take care of ourselves. We can take care of the planet. We can maintain a healthy space and understand what we're doing as we become more numerous and powerful.
Yeah, that's a beautiful way to put it. It's like, I mean, I'm sure Abe Lincoln said this, but like everybody else, like pretty much every really intelligent person through history has probably said something along the lines of like, if you want to make good decisions in the present, then learn from history, right? And
we do it every day.
That's the thing. Like, we're trying to make good decisions within our kind of anthropogenic society. But when you want to think about, okay, how are we going to affect this entire planet and the natural history that's on it, then you have to look at not just our history as people, but like the entire history of the planet.
Yeah. Yeah. Because our perspective as individuals is so small. It's so short. What we see in our lifetime is so limited. Yeah. And our view is so narrow. We really need that bigger picture that that geoscientists can bring. So I think, I spend a lot of my day looking at bat teeth, looking at fossils and thinking about what does this little bump right there mean, right? And what can I say about that? And, I can talk to people about that and they're zoned out. They'd like, why are you doing this? This is so esoteric. This is like ivory tower nonsense. But it isn't really. It is directly relevant to how we interact with the world and what we know about it. Yeah. It's just, we accumulate that knowledge in kind of a funny way.
Something I wanted to mention a couple minutes ago was that Africa and places close to the equator seem to still have a lot of the species, like the large megafauna and species that were around, during the Pleistocene Holocene and late or early Holocene, Pleistocene. And even in like the Amazon, like they still have these huge anacondas. You have huge caiman, jaguars. It still seems very, very wild. Is there like a sensitivity, like things closer to the equator didn't feel so much of a climactic shift?
That's a really good question. The changes that are occurring in the late Pleistocene across the globe are not equal. And in some places, the changes are more dramatic and more rapid and more obvious than others, right? And that was part of the overkill argument from the start was we were in Africa for so much longer. We were in India for so much longer as a species that the animal community around us wasn't as naive. It knew us. It knew the danger of us. And so we couldn't as easily wipe them out. Right? But I don't know. make what you will of that argument. I don't think senior matriarchal mammoth is going to be that naive about some big bipedal thing that it's never seen before or saw once and had a real bad experience, right? I think these are smart creatures. They see something funny walking towards them in a threatening manner. I don't know. That naive argument, I think, is overplayed. And now we know that we were here in North America with these animals for a long time. So could they have really been naive? But there is this kind of differential impact regardless of that naivete argument. And there are still big animals. So why did these things make it through and not others? I think it's really part of what we lose when we don't have the ability to look into the past is we look at the present as like a given. Mm-hmm. Of course, there are moose. Of course, there are grizzly bears. That's what's supposed to be here, right? But I didn't have to be that way. It's a set of circumstances that led to those big animals being here and other big animals not being here, right? There were spectacled bears in Texas. Why are they not here? Why is a moose, right? Why was the moose? They're huge animals and have a lot of the same ecological constraints that other huge animals that went extinct had, right? They can only make so many young a year and it takes a lot of energy and investment, things like that. They didn't go extinct, right? So there is a differential impact even in places like North America or Africa where certain animals were lost and certain other ones weren't. And if we just look at it from our modern day perspective, it's, yeah, of course there are rhinos in Africa and there are moose in North America, not vice versa. But if we look into the past, you start to realize it didn't have to be that way. And there's actually a reason. There's something about those different species that allowed them to persist or not. And then I think our present view is also altered by just what we've done to the planet in the past 100 years or 200 years since we've started documenting what animals live with us, right? So Texas made an effort to do this around the turn of the 20th century. They sent a team of biologists, well-funded, across the state to determine what lives here, what mammals live here, what reptiles live here, etc. And the mammal report was huge, right? They showed us what lived across the state. And if we look at that report, there are jaguars across the Edwards Plateau in 1900. There are ocelots, right? Just a county away from us here in Austin.
Oh,
yeah.
Wow.
And into the 20s. The last jaguar on the Edwards Plateau was here in like the 40s. So and we don't think about that, right? We don't. Man, I think most people in Texas
that's crazy.
do not think about jaguars on the Edwards Plateau, but they were here. And we've removed them pretty recently. We've made them regionally extinct because they're threatening to us. They're scary. They eat our livestock. They could carry away a child, right? I mean, I get it. We persecuted these carnivores and other big animals, and we've made these changes that are recent in history, but are because of our own short lifespan as a human individual. They actually seem quite distant and far enough into the past that in general, people don't even know some of these animals that were here just a century ago. And so it seems that disparate effect of this extinction event, the result of it is even harder to get at and to recognize and observe because we just keep modifying the animals and the landscape and the environment over time, all the way up until the present day. Yeah. So it gets kind of hard to see the past clearly because we're starting from a present that is already so altered.
Yeah. And also, we're just looking at the largest mammalian creatures even in the conversation we're talking about. But we're not even like, I guess there's almost a selection bias in like, all of these large mammalian creatures are gone, but what about the small reptiles?
Yep.
What about the bacteria? What about the plant species? What about the snakes and birds and things like that? Like the smaller organisms that maybe stuck around.
Right. And that's a big part of the argument for climatic change driving these extinctions at the end of the Pleistocene, is most of the small animals that were alive then are the same species that are alive today. But in a lot of cases, they changed too. So there were small animals that were present in this region in the Pleistocene that are absent today, that became regionally extinct. And this happens all over across North America. The composition of the animal community changes because lizards, snakes, birds, small mammals, extant species change their distribution around the same time as these big animals go extinct. So it's not just big animals going extinct. It's actually some big animals and other big animals were fine, right? Grizzly bears and moose, jaguars. And then it's not just big animals being affected, it's small animals too, and of all types. And there's actually a similar pattern with plants, where we see plant communities in the Pleistocene that have no modern analog, where you have species living together, species of trees, for example, living together, that in nowhere in North America do they live together today. So we have a completely different sort of community composition that also changes at the end of the Pleistocene. And so what is pulling that thread, right? Is it climate change? That's a big argument for climate change, is all of these things are changing. The whole system is changing. Yeah. But you could think about it as possible that climate is changing and human hunting is magnifying changes that are being initiated by climate change, right? So where we maybe are killing mammoths, right? There's good evidence that we killed mammoths and consumed them. And they do reproduce really slowly, even slower than us. They invest a lot of energy into every offspring. And so if you lose a couple breeding years, that's a really bad sign. Your entire population could start down a slide towards extinction. And so maybe we're doing that. And climate is changing. So maybe we're acting to pull out a keystone species at the same time as the entire climate system is shifting. And so the two together, right, could then start to influence habitat diversity and other things that alter, well, these little animals can't live here. This tree is changing where it lives because it's actually reliant on these, right, proboscideans to disperse its seed or something like that. Think of every complexity in an ecosystem, every line in a food web. That's really what we'd like to know about the past, and that would show us that sort of complex dynamic is occurring, but it's really hard to actually reconstruct all of that.
Yeah. I was reading about the European steppe homotherium and how its anatomy was kind of like a cheetah almost. It had a very large nose, had long, slender legs. It was very much built for running, and its visual cortex and its brain was very big. So it was kind of more of a daytime predator. So I'd imagine that this predator is really, really adept at running through this savanna-like steppe, right? And chasing after these huge, whatever, pronghorn or whatever other kind of antelope type species were around in that area. And now you remove the mammoth and mastodon through either climate change or human hunting or whatever.
Right.
And so, like I mentioned earlier, those grasslands turn into taiga forest. And now you have this savanna predator that no longer has a savanna.
Yeah, right.
And there's nowhere for it to go or for it to hunt its food, and it can't run through the trees. You know, it's not built like a wolf or a jaguar or something, you know?
Yeah, and we know those kind of complex dynamics characterize ecosystems today, right? The presence of different species influences the behavior and capabilities and possibilities of other species. There's really complex interrelationships in natural systems. And it must have been that way in the past, too. There's no reason to assume the past was any less complex and less intertwined and interrelated. But, man, it's just all those different threads are really hard to disentangle and actually see that, right? That scenario that you described, to actually demonstrate that exists, even though we can easily infer that those dynamics must have occurred. It's really hard to document.
So, focusing on Texas. So, let's fast forward or rewind. Let's rewind, 14,000 years. You have this neotropical Texas, especially near, let's say, Houston-ish, neotropical belt. And then you have like marshes and kind of where the panhandle is.
To some extent.
Yeah. Okay, so I guess instead of me just taking a wild guess at things, can you explain what Texas looked like 14,000 years ago?
Oh, yeah, that's hard. That's actually hard. But I think in general, it seems like it was a slightly nicer place to live. It was less seasonal, it appears, than it is today. So the idea of these hot summers, right? These summer extremes were pushed down. The winter extremes were pushed up. So rather than oscillating in temperature and moisture throughout the year, is much more kind of even throughout the year. It appears. But that's hard to get at too. And then the other thing that was like today was it seems like different parts of the state had different habitats. But the extent of that kind of provincialism, that variation in regional habitats, the extent of that is really difficult for us to figure out. But that's kind of a hot topic now. Yeah. And we can see some of it, right? So certainly the coast was further out. There's so much water locked up in these glaciers on the northern hemisphere that oceans are lower. That's one reason you can get from Asia to Alaska in the Pleistocene. So the beach, right, was actually further out into the Gulf than it is today. The Gulf was lower, so there's more land exposed. This whole continental shelf is actually terrestrial. And so there's this wider Gulf Coast that leads from Mexico kind of east into Florida. So think about the end of Florida, right? It sticks out way down towards the Caribbean, and then it makes this big thumb kind of down. Mm-hmm. And Texas is over here, right? Kind of coming down like that. So just extend that whole coastline out more so that this thumb isn't sticking out nearly as far from the rest of the Gulf Coast in Mississippi, Louisiana, Texas. There's this broad continental shelf that's exposed, and animals in the neotropics in Mexico could simply traverse over to Florida. Mm-hmm. And so you have this kind of what we think of as a neotropical corridor, where you have all of these animals in Florida in the Pleistocene and along the Texas coast that are a lot like animals in Central America. And it's because it appears there's kind of this belt of habitats that extends across the Gulf Coast and into Florida. So you have this big kind of neotropical land bridge sort of going from Central America to Florida. And it's really neat because as you move north from southern Texas and Florida, you start to lose a lot of those animals really quick. And so we're talking about things like capybara, giant extinct capybara, spectacled bears, which there's a spectacled bear that lives in the Andes today. Things like glyptodonts, these giant Fiat-sized armadillo-like animals with these huge dome shells and like armored tails.
It spikes at the end of their tail too, right?
Some of the South American ones did have kind of interesting structures at the end of their tails. Yeah, kind of like a stegosaurus, sort of apparent weapons or display objects at the ends of their tails. Yeah. And you have this set of animals that are common in Central America and in some cases South America that extend north into southern Texas and Florida. And so it seems like you really have this neotropical kind of warmer, wetter portion of North America, much in the same way it is today, right? You get into southern Texas, you get into Florida, into southern Louisiana. It's different than Missouri or Kentucky or Oklahoma. Like it's wetter, it's warmer, it's different. So that some of those differences were there in the past. But as we move north and across the state, it's a little bit harder to discern them. And as we move east and west across the state, it's a little bit harder to discern them too. In part because of our geographic, the scope we have of our fossil occurrences is limited in parts of the state. So in East Texas, right, it's forest and it's really wet. It's really hard to find fossils. And in the west of the state, it's really hard to find fossils too. In both places, it's kind of a confluence of not great preservational environments in the past and not easy to find and see stuff below the surface today. Mm-hmm. And so there are kind of splotches across the state where we have really good samples. And most of those show something like a grassland, some type of grassland. Maybe it's changing over time to where in some intervals it's more like a savanna, it's more wooded, where you kind of have trees and interspersed in that grassland. And in other places it seems a little bit more like it's more open, it's more plainsy. But the floral communities were probably different. So it's kind of, you can't really imagine any one modern setting. It's kind of a combination of multiple ones. So we could think about an open grassland setting in some cases, maybe out in the Panhandle. But it's not the short grass like what's there today. It would probably be big, tall grasses, right? And
how tall are we talking?
Oh man, like you probably taller than you'd want to wade through. Tall enough that you like, I don't want to go walking through that. A meter or something. There are still some tall grass habitats in the Great Plains, especially up in the northern Great Plains, that are probably comparable. You can see some habitats like that in present day India, in some of the national parks there, right? These rhinos and water buffalo, and their heads and shoulders are kind of peeking up out of this tall grass, like really tall grass prairies. And then again, a lot of the state was wetter. So even in places that are pretty dry today, like the Panhandle, there were rivers flowing through those drainages. There were marshes along the edges of them. There were more lakes on the surface with marshes along the edges of them. So it's definitely a different past, but it's not like an alien past. It would be something, a lot of habitats that are familiar to us today. They're just in different places and they're kind of shaped a little differently, or they have different aspects, or they have things together that don't occur together today. But a lot of this is stuff we would recognize, right? There is a gradient in temperature. There is a gradient in moisture. It's that's one thing we want to know now. Once we recognize that, then it gets harder to make a one size fits all driver of changes in the animal community. If there's variation, right, in the animal community, in the habitats and the environments all across North America, then how did any one trigger affect all of it in the same way? And it's one of those things that we need to document first to understand what the outcome was. Mm-hmm. Because maybe that species didn't go extinct in this region at all. Maybe it was never here because of this sort of regional variation, this provincialism, just like that exists today, right? You would never expect a grizzly bear in Florida. But if you don't...
something goes wrong at a zoo.
Right? Or some dude that, right, owns 3 grizzly bears out in...
Oh, yeah. Good knowing Florida, I wouldn't be surprised if...
But if you don't know that, then you just show up in Florida today as some alien biologist, and you think, wow, I don't know what happened to the grizzly bears here, but there is not a single one left. That's totally a false conclusion. And so now that we can kind of see that this provincialism existed across Texas and North America, it's a big effort to document it, because that has an impact on how we understand that extinction event. Some of those animals may have been absent from certain parts of the continent, not because they went extinct at some earlier interval and we haven't found their fossils yet. They just weren't there.
Mentioning Florida is a really interesting topic. I would imagine being an alien biologist going to Florida, you would be very confused as to how things like Burmese pythons, where are they? Usually like Indonesia?
Well, I mean, there used to be a country called Burma. It's just not called Burma anymore.
Oh, okay. Yeah.
But it's next to like Thailand and Vietnam and stuff. It's Myanmar now.
Yeah. Like, how did these snakes get all the way here? And there's other some of the iguanas that are there, very non-native, but
full of exotic species. Yeah, Florida is a mess.
To that idea of rewilding, are there any, I guess, species that like maybe we've introduced today in areas, maybe like Florida or maybe elsewhere, that were there in the past, but now there's just not the right ecology to even like support them anymore? Because like maybe there were large snakes like Burmese pythons in Florida when it was neotropical and there was more land mass, right? But there were also the predators in place to keep those populations in check. Right?
Yeah, right. That's hard. The one that comes to mind, I guess, is horses. There were horses in Western North America in the Pleistocene, and if we saw them, we'd say that's a horse. They weren't that different. Their teeth are the same. Their skulls are the same. Their diet must be similar. Yeah. They're horses now, horses then. These horses that are there now are feral, right? They're a domesticated species that we brought to North America, and some of them have been able to make a living without us. Yeah. Feral. But if you go to these places, it's a mess. These horses are overpopulated. There's too many of them for the resources that are available for them to consume. So there's too many horses for the available amount of forage. Yeah. And so we take on this role of managers, right? I was in Arizona last year or the year before, and there's all these horses in the desert. And they're making a mess of the places, the habitats that do exist that have enough plant food for them, like along riparian areas. And in other places, people are bringing out bales of hay and just like piling hay up for them and like making these like feeding centers for them. People that feel sorry for them, right? That they don't have enough to eat, that they're suffering out there. And so they are right there in big numbers. They're overpopulated because there's no big carnivores left in the West to kill them. Right? We've persecuted mountain lions. We've persecuted gray wolves. There's not jaguars in most of the places that there were jaguars. No. And then these horses who were there historically, right? There were their horses historically in, right, natural history in the Pleistocene. Yeah. And there are horses today, but these horses can't really make the same living as those horses that lived in these same regions in the past. Those ecosystems that supported those animals is not really there in the same way. Yeah, some horses live out there, but they're not living there in a way that would be sustainable in the absence of people over geologic time. Mm-hmm. So that's certainly one where, yeah, species are similar past and present. Horses were there in the past. They're there today, but it's a really different sort of dynamic and situation.
Yeah. So you were saying that during the Pleistocene, when there were horses there, they were preyed on by wolves and...
Well, there were a myriad big predators, right? So they would have prevented this sort of overpopulation problem that is happening today. Yeah. And that just the habitats would have been different. Those horses were there because they evolved with those ecosystems over time. The horses are there today because some escaped from, right, our barns and pens and corrals. They can make a living out there, but it's not actually a balanced sort of living where they can continue to exist with this landscape and these environments and these other animals for generation after generation after generation, right? This is not a sustainable way of living.
Yeah. This might be a bit of a vibe switch, but more of a fun question.
Oh, yeah, good.
I want to ask you, what is your favorite fauna? Paleontological or modern day?
I don't know.
Or you could give like a top 5.
I really like the Great Plains. So that's big for me in the present day. Right? The openness and the aridity, I think, has made a really interesting animal community. And I think one way it's interesting is that it's subtle. There is this beauty to it, this wonder to it that can be overlooked if you're not looking at it in the right way, if you're not inclined to pay attention to it. Right? You just look at this place and see it's empty and decide it's empty. But if you're more open to it, if you're more patient, there's so much life there, and it's such interesting life. I don't know. I really like that landscape.
Mm-hmm. Yeah. Most people, myself included, when I drive out there, I just think, oh, this is flat wasteland. And it kind of stinks like eggs, and because all the Permian Basin. All the oil,
yeah, right, yeah.
But yeah, I would imagine, especially if you spend a lot of time in it, has a lot of beauty.
Yeah, there's a lot there.
Mm-hmm.
Yeah, it's really fun.
What about favorite? I guess like animal in specific.
That's hard. Yeah, people ask me this a lot, and I usually kind of punt by saying it changes over time. Like, who am working on right now that has me all jazzed up? Okay. But even that, I don't know. Actually, I'm kind of on giant tortoises for the moment. The past few days.
And those were roaming around Texas
right.
too, right?
Yeah, these huge giant tortoises, like Galapagos things. Some of them, right, as big as this table, both in length and in terms of height, up from the floor. Huge tortoises. Really, just kind of. So I know they were there. I know they were in North America for a long time, and they still seem kind of exotic and foreign and novel to me.
Yeah, you don't think of that when you think of North America.
No. No, they're really neat. There's actually a great specimen just over here from near Corpus Christi.
Oh, that thing is
monster
huge.
Tortoise, just huge.
Oh my gosh!
And he has a couple of his back legs with him still, and some armor that was in his skin. It's a really cool specimen. But yeah, these things were around, were apparently abundant. Really neat.
Yeah, that is in Corpus Christi.
Yeah. This one is from Corpus Christi. Okay. Near there. There was a sand and gravel pit that was operated in the first half of the 20th century, maybe the first quarter of the 20th century, that produced just an amazing late Pleistocene fossil assemblage.
Yeah, that's another cool thing about paleontology is like it's I would kind of think of it as like you find a fossil and you're really lucky, and then like, you know, all of these finds are, you know, from separate areas all around, and you're just lucky to find them. But it seems like the more I talk to you and from what I've seen myself, a lot of fossils are found in like a big spot where there's just a ton of them. Like, where it was like a really good way to bury it. I mean, you might be able to correct me if I'm wrong.
Yeah, I think they're everywhere.
Okay.
But it's hard to ever notice because it's just a bone or two, right? So you could dig a hole here and never see it, and there's a bone right there, and things like that, where it's just it's too diffuse for us to recognize it. So it seems like there's nothing, and then in other places they're concentrated by the behavior of water. Maybe by the behavior of other animals, maybe because of certain conditions that were very localized, right? A certain landscape type or a certain, right? Just think of anything, certain set of conditions, certain chemistry, maybe even, where material is going to be concentrated or preserved or accumulated. And those are our fossil sites, right? Because it's worth spending a lot of time and effort and energy on, because it's not going to be just one or two. There's a lot there, right? These places that are more diffuse where there's just one or two. Yeah. We don't really have time to do that. It's not going to give us much. We're going to spend a lot of time on it. And really, it's not going to give us that picture of a system. It's just bits and pieces. And maybe sometimes those bits and pieces themselves are just so special that they're worth it, right? Maybe you get a giant tortoise like this that as one individual is worth all the time and effort. But if we really want to understand natural history, we need that big community picture. We can only get that big picture in places that fossils are rich, right? Because we need to see all the animals. We need to catch the rare ones and the common ones, and maybe even be able to recognize that pattern that, yeah, these things just were not common. These things were really common. There's a lot of them. We need to place them in time, and you can only do that in certain places where, right, it was Goldilocks. Everything was just right. Some process concentrated bones of animals in this spot, right? When we kind of get back to the start of the discussion, and talk about caves,
full circle
right?
Here. Yeah.
So we've got to seek those places out. In this part of the state, that's caves. Got to go caving.
Yeah. It is really, really cool, like you were saying, how the environment that kind of gathered all those fossils together, or like the way that those fossils form or the space that they're in, can tell you a lot about kind of the story behind everything. Mm-hmm. Like, I forget if it's Natural Bridge or Inner Space, there's this like rock that they lifted up and they found all of these bat skeletons under the rock, right? And that was sort of a rock like with a bunch of bats on it, just falling down, crushing all the bats, and they just got preserved there.
Yeah, right. Then in that case, it's just a fluke of history, right? It's not that anything accumulated those bats. The bats accumulated themselves. They like living together, so they all, right, are concentrated through their own behavior. And this weird kind of moment in history created something really unique. And that's so much of what the fossil record is unusual things happening, right? Really unlikely things actually occurring, and maybe multiple unlikely things occurring all together. But in geologic time, right? There's so much time for lots of weird things to happen. And yeah, in inner space, that what you're talking about is so cool. It's called Bat Breakdown. It's one of the Pleistocene sites in inner space cavern, and you can go see this. You can't see the site directly, but you can see where it is. You can see it from the public tour, and pretty much exactly what you said happened. There was, during the Pleistocene, maybe pre-late glacial maximum, there was a colony of free-tailed bats roosting in that room, in this one room at the north end of the cave, and the ceiling collapsed. This is normal in caves. It's not super normal, right? You shouldn't not go to inner space. This will not happen. I can almost 100% assure you that the ceiling won't collapse, but this happens in caves. That's one way caves get bigger, is water kind of weakens parts of the bedrock and slabs of ceiling can fall to the floor. And that happened at some point in the past and killed part of this colony, this free-tailed bat colony. And we know that because there's this slab, it's like 10 meters across or something at its maximum dimension of bedrock that's laying on the floor, but it's not directly on the floor. It fell onto like a bench of limestone that's kind of protruding from the floor of the cave. And so part of it fell on the floor and part of it is leaning on that bench. And so you can actually see the underside of parts of this slab. You can get underneath it in places, and other places you can kind of crick your neck and stick your head underneath it, and you can see the underside of this slab. And a lot of the underside of the slab is covered by sediment. There was a deposit forming beneath this part of the cave that the slab fell onto. So it fell onto dirt. So you clearly can't, right, see through the dirt and see the underside of the slab. But in places, the behavior of water in the cave has eroded sediment away. So you actually you can kind of lie down on your back. You can crawl underneath in places. You can see the underside of this slab, and it's covered. It is coated. It's coated. It's a crazy thing to think about, but the underside of this big piece of rock is coated literally with bat skeletons, not bat bones, but bat skeletons. And in places where they're well preserved, because it varies across the slab, in some places erosion has modified them more than others. In places where they're well preserved, the bats are in whole skeletons with their wings folded up and their head, the back of their heads consistently pressed against the slab, and their feet stretched out away from them. So they're kind of in this position, which is how bats roost. And it's just densely coated in bat skeletons across the underside of the slab. It must be thousands of individual bats that were caught, right, in just this freak accident, this freak moment in geologic history. But it's cool, one, because, wow, you ever seen anything like that before? No, most people haven't. And it's cool too, because it means that we can look at these bats as members of a population, members of a colony who all lived together, who were related to each other, who were there using this cave in the same way at the same time. We know these bats knew each other, and so we can start to ask questions about, well, what's the composition of this community? Is it all adult? Is it all juvenile? Is it a mix? Are there no juveniles? Are there pups here? What were they having babies in this cave? Was this kind of like a stopover cave? Was this someplace like Bracken Bat Cave, where it's a huge colony that's extremely important to the survival of this entire species in this continent? Or was it kind of just a way station as the bats moved from one region to another across North America? We can pose questions to that sample in Inner Space Cavern that we simply can't anywhere else on the continent.
Yeah, usually like your sample size is just
Big
blown up by
size.
what, like, 1,000% at least,
Yeah.
right? And usually when you're digging for fossils, I mean, you're finding one specific representative of an entire population that had the perfect circumstances in order to become a fossil.
Yeah.
Most of those bones are just going to degrade, wash away, be eaten.
With bats, it's really it's hit or miss, right? So you get outside of caves and it's really rare to find bat fossils. Yeah. It's really hard to get that one bat falling out of the sky right into the right spot, right, where his bones can get preserved. But in caves, it can be crazy with bat fossils. And in part because when you get these big colony bats, these bats that live in big colonies, right, hundreds of thousands of individuals, they start to make their own ecosystem in the cave. And there's so many individuals, it's like a city, right? It's like a city. Humans, right, in Austin today, somebody is being born, probably lots of people are being born, several people at least, and some people are passing away. And it's the same thing in these bat colony caves. And it's enough individuals dying on a regular basis that these big colony bat caves develop colonies of flesh-eating beetles on the floor of the cave. There's enough death to support colonies of beetles that all they do is consume bats that fall to the floor because they're sick, they're too old, right? Something's wrong. So you have hundreds of thousands of individuals maybe in a cave for a few thousand years. You can accumulate an amazing amount of bat bones really quickly. And you have that in a lot of caves in North America, west to east, north to south. But it's attritional. It's accumulated over time by individuals who may have been millennia apart, right? And it's their bodies have been taken apart as they hit the floor by these flesh-eating beetles. So you have all these different bones of all these different individuals accumulated across time, all mixed up. So it's a great sample in terms of size and in terms of being able to look at variation in terms of individuals, right? You get the big ones, you got the small ones, you got the adults, you got everybody, and you got lots of them. But what you're missing is the relationship between individuals and the relationship between individual specimens. And that's what's so cool about that inner space assemblage, is the bones are still connected to each other. This bone is connected to that bone. It was in the wing of the same bat. And this bat is next to that bat. They were next to each other when they were alive. And that is really, for any time period or any fossil animal, that is really rare and special.
Yeah. So for the possibility of you caving and ending up like that bat is something you're not worried about at all.
Well, the caves collapse. Parts of the caves do change over time in a way that would be hazardous for a human.
Okay, so walk me through, like, what does a cave expedition like that kind of look like?
Well, it really depends on the cave.
Yeah.
Right? But in a lot of inner space is different, right? It's a show cave, right? People can go see the spot where these bats are because there's a paved path and there's guides and there's lights, right? There's all this stuff. There's this infrastructure. But in wild caves across the region, there's not any of that. And that's when it becomes a little bit more dangerous. The wild aspect of these caves is more of a hazard than part of the cave breaking off and falling on me. That's happening over geologic time, right? That slab that broke and killed those bats happened 20, 30,000 years ago, and there's nothing on top of it, right? That part of the cave hasn't collapsed again since. So the idea that that's going to happen to me on any given day, it's right. I'm probably more likely to win the lotto.
Yeah. Which is incredibly unlikely.
Right. Is almost impossible.
Big scam for anybody listening. Don't buy lotto tickets.
But then you think about other caves these wild caves where they have open sinkhole shafts that go down 100 feet or more that you can fall off and go down that shaft uncontrolled. You could get into some of these water caves where there's bad air because there's too much carbon dioxide buildup and not enough exchange with the surface. You could get into places where the water is moving in a way that is hazardous for you, right? It could be raining on the surface and you don't know it. And all of a sudden the current picks up and you're underground in a confined space and maybe it floods. Maybe it carries you. Maybe you just hurt your ankle and can't quite manage to get back to the surface in the same way that you went down, right? So it's more kind of those normal sort of hazards of doing anything outdoors in a natural setting. That's where the danger comes in caving. And that's a danger we can manage, right? With training and safety techniques and being responsible. And that's what we do, right? I think it's if we're going to talk about danger, I think it's really important to note that that we need to be safe when we go caving. Caving is something that we do with friends, something that we do in a controlled manner, and especially when we get into these wild caves that we do with a lot of training and forethought. And so I would never bring somebody to some of these caves if they haven't had that training before, and I certainly would discourage people from going into places like wild caves across Central Texas without training and a lot of forethought.
Yeah. What is it? What are some of the thoughts running through your mind whenever you're like, let's say like shimmying through, a space that's, just as wide as your shoulders are, but you have no room to really move your arms or it's just pitch black. What are the thoughts going through?
Well, I mean, it's not pitch black because it better not be because otherwise I can't see where I'm going. Right. And then my thoughts are not
grim.
Great.
Yeah.
If it's pitch black, somebody needs to come get me because I can't. So I have lights on, right? So I can see where I'm going. And I don't know, you're probably going to be disappointed with this answer because my thoughts are very, very, very practical. They're usually like, ouch, that rock is poking me.
Yeah.
Ow, this is really uncomfortable. Or like I'm snagged on something and it's ripping my shirt.
Yeah.
I don't want to move this way. How much longer is this passage? It's all kind of thinking about the discomfort of it. That's usually where my mind is. And it's not really on like the claustrophobia part, right? I think that's where people expect it to be, but I don't know. That doesn't get me as much as just like, gosh, this is the weirdest position I've ever been in. And I hope that the end of this is right around the corner because I'd like to stand up.
Mm-hmm. And so you're very present in the moment when you're going through a cave, and you kind of offload a lot of the philosophical thought towards maybe if you're in a more comfortable position or after you've gone on the expedition.
Yeah, I mean, I think about the practicalities of it. You have to do it responsibly. Yeah. But I think about them in a sober way. I need to attach this correctly. I need to do this. These are serious moments, and I need to focus and do that in the way that I've been trained. And the rest of the time is, it's just kind of, wow, that hurts. Geez, I'm tired. Boy, I'm sweaty. It's like anything else.
That's what I really enjoy about geology in general, is how fieldwork is very grounding. No pun intended.
What do you mean by that?
Like, you have to be present in the moment. I feel like a lot of the time as an academic, you are kind of operating in the space of ideas and like faint images inside of your head, and you're trying to create things from your own mind. But when you're out in the field, what's in front of you is what's in front of you.
Yeah.
And it's very practical, like you said. It's like, okay, one step in front of the other. Like, I was doing some field work with, have you met Charlie Kieran's?
Yeah.
Yeah, Charlie Kieran's and a glaciologist at UTIG, Ben Kiesling.
Yeah.
And we were looking at beach deposits, like karst beach deposits.
Cool.
And I like, yes, you can think of like the broader science and the geologic story behind this, or like what you're observing, but a lot of times it's just like, man, I'm really hungry, and I'm so looking forward to lunch, and then you're just kind of going through it because it's very taxing, it's very physically demanding.
Right.
And also a lot of the time you're like, tensions can be kind of high in a group when you're in a stressful environment.
Right.
And you don't get that. And I think in other professions, I mean, you do, depending on how much field work you do, right? But it's geology is such a cool balance of like, you still get to experience this kind of like almost aloofness of being, when you're writing a paper, you're constantly thinking about the ideas, and you're trying to read all these papers, take in all this information, and then you, I guess, don't focus on what's right in front of you too much. You're just constantly thinking about this problem. But then you're kind of thrown into the opposite spectrum of that. And it's like, you're in the field. This is what's right in front of you. This is what I have to do. Man, this hurts. My back hurts.
Yeah.
Whatever. My feet hurt. The feet were a big thing when I was walking around. Jeez.
Yep.
Yeah.
Yeah, I think that's fun. It's really, it's lucky to, I think, to get both of those scenarios you're talking about. It's really nice to have that contrast and to be able to get out in the field and be physical. And your brain acts different. There's different chemicals going through your body, and it's great to have that change of pace.
I feel like I don't know about you, but I feel like my personality changes a little bit. Like you were saying, like my brain is operating in a different way, different chemicals, different stimulus. And I feel, it's just like harder to manage stress. It's like, it's just harder to do things, I guess. Like, things I think bother me more when I'm in the I don't know about you.
Yeah, I see what you mean. I think you learn to deal with that. You learn to, you learn how to manage that stuff.
How about wet caving? Like, what is this? What is it like to snorkel through this cave? And I guess, we could start with that. But also, like, what is it like to think I might be like one of the first people to ever even look at this?
Yeah, I mean that's why so many cavers do what they do is that discovery potential, right? They want to go caving because they are likely to encounter places a human has never been before. And that is just
pioneering,
that's pretty neat.
Primal human instinct. Yeah.
Yeah. There's something about that. But these water caves, so inner space, right, and Natural Bridge are dry caves. They're actually really humid and muddy and fairly wet. But they're dry caves in the sense that they don't have standing bodies of water for the most part. You get into the lower levels of Natural Bridge, and they have pools in some places. But there are some caves in this region that are essentially underground rivers. They're these big, long, tunnel-like caves, often with little branches of smaller caves coming off of a main channel, a lot like a river, right? You have little tributaries feeding in. And at the end of this big tunnel is a spring. So these caves are essentially parts of the aquifer system in the region. They're portions of the bedrock where groundwater can accumulate and it can move through. And a series of historical events have occurred where there's kind of been a little nick point that allows water to escape out of that level of the bedrock, and all of the other water that's under pressure starts moving towards that escape point, and it creates these long tube systems that then fill with water that wants to go out and be a spring water. And they're really neat. I think they're really neat. There's something about this combination of rock and water that is just really magical. I think there's just the way it looks is really pretty to me. I don't know. It's really an interesting environment. In part, it's interesting because there's animals in that water.
Salamanders,
yeah. Little invertebrates, crayfish, all kinds of little creatures. So there's life down there, and it's like you're in a different world. You can come from the surface and somebody's ranch, right? Just out in a grassland, normal everyday Central Texas, and all of a sudden now you're below the ground. You're in this cold water, clear water with these creatures that are not on the surface. It's really neat. I don't know. There's just something about it. And the water's flowing, so that it's not just that you're in this pool. You can feel that you're in this system, and the water's cold. So it's essentially it's Barton Springs, but you don't have the sun, right? And I don't know. However, I don't know. I think this is how most people do Barton Springs. I don't know about you, but I like get there and I'll sit in the sun for a little bit, and then I get in the pool, and then I get out and I warm up. And when I get too hot, I get back in the pool, right? Because every time I get in the pool, I'm like, oh, it's cold. Oh, it's cold. And I kind of have to walk in. I get to my belly button. And I'm like, oh, I don't know. Okay, I can do it. It's cold water. It's like 68 degrees. And that sun helps me kind of manage the difference between 100 degrees outside and 68 degrees in the water. But in these caves, it's 68 degrees and there's no sun. So we have to wear wetsuits. Otherwise, our body temperature just can't maintain it. So you wear a wetsuit because the water's cold. The water's really clear. It's very pretty. It's fairly clean, at least in terms of its appearance. And the reason I'm going into these places is because some of these water caves, the floor of the stream has bones of Ice Age Pleistocene animals strewn across the bed of the stream bed. So we can actually snorkel through this water. And as we're going, right, we're snorkeling along, there goes a little salamander, there goes a crayfish, there goes a little sort of roly-poly aquatic cave animal. And here's a mammoth tooth. Here's a saber-toothed cat bone. Here's a camel bone. Here's, right, this, that. And we can just pick them up and we carry these mesh laundry bags on our belts. And so we bone in there, right? So we can carry these bones, but we're not carrying water with us. We're not carrying the weight of more than just the bones.
Imagine it gets pretty heavy.
It does get pretty heavy because the water is really calcite rich. It's really mineral rich, like we were talking about earlier. And these bones are heavy because they've in some cases they've filled solid with calcite. And so they pile up quickly. But we can leave them behind on the banks and continue because we're going to come back the same way we went in. And so we accumulate these bones over time as we move through the cave. And what's really neat about it is that the animals that we encounter in these fossil assemblages are different than the animals that we encounter from Ice Age deposits in the dry caves. And it's consistent. And so I don't entirely know what's going on with these water caves just yet. Yeah. It's still an emerging picture. Nobody has explored the Pleistocene fossil record in these water caves before. But it appears that these water caves are giving us a different view of the Pleistocene, a different window, either into a different set of habitats or maybe a different time period than the view that we have through the dry caves. And this region has a really incredible, really robust, extensive, and important Ice Age record from dry caves. It's all from dry caves. Nobody's ever explored these water caves, and we're starting to do it, and it's showing us something different. It's showing us animals that, based on the record from the dry caves, we always thought those animals aren't here. They were never here.
It's fascinating.
But
absolutely fascinating.
There they are.
Yeah.
And so to get to them, it's a lot of work. We have to rappel down these sinkhole shafts. We have to squeeze through little tubes. We have to crawl then horizontally at the bottom of these shafts and often go down through another hole in the floor again. And that pops us out into cold, flowing water, water that is sometimes really shallow. And maybe we're crawling or stoop walking through it. Really kind of uncomfortable maneuvers. In other places, we're in these big canyon-like passages with water so deep that we can't touch the floor, and we just have to swim until the next place that we can stand. And all sorts of different variations of topography and kind of room sizes in between there. It's really physical hard work, but it's a ton of fun.
Yeah.
And it's really great in terms of the science that's coming out too.
That sounds like a absolutely unique experience. Like, I can't think of anything that would be
it's wonderful
similar to that. There has to be, like, I'd imagine those fossils get heavy after a while, and then you can't, like, there's only so much you can put on you without, like, I guess, detrimenting your ability to swim. And then also, like, some of these bones are pretty big. Like, how do you get that out of the cave whenever you've kind of done some spelunking and like shimmying, and you're going through these really narrow passages to even get down there?
Yeah, it's hard. That's one thing that limits us. At some point, we're like, we've got enough fossils. We need to start heading back because we just can't carry more. So let's stop for the day. But we have big bags, right? So I have like a pack that's probably this big. And I'll bring that. I'll bring another one similar size sometimes. And yeah, we try not to carry all of them all at once until the end, right? At some point, that's it. Like, we're back at the exit, close to it. Yeah. There's nothing we can kind of keep shepherding along now. Everything has to be concentrated and put together. Yeah. And it's just hard. I don't know. You move them along. You're motivated by just the discovery and everything about it. But when we get to the sinkhole, it becomes a little bit easier because we don't have to carry these bags up with us. One person can go up to the top, and we can attach a carabiner on a knot on the end of the rope and put our packs on there. and pull it up. And it's a lot easier than having that dangling from my body and as I ascend on that piece of rope. So pulling it up is pretty easy. So once we get it to the sinkhole, it's not bad. The hard part's over. The bad parts are really the worst parts are when we have to be on all fours. So we're crawling along, kind of have to crawl a few steps, reach back and grab your bag and kind of gently move it up to you, crawl forward again. Just because you can never really use your full body strength. You're in a crouched kind of on all four position. You can't really get your legs and your back and your arm all behind this big 50, 70 pound pack. Yeah. And it's tedious too. So not only is it hard, but it's taking forever. And that, like, those two things together, that's when it starts. You have to persevere, right?
Yeah,
and just tell yourself, like, come on, a little bit further.
Yeah, you're in just like this closed space, and that probably doesn't help at all. I mean, it seems really unique because a lot of the fossils that are around us right now, you can see the plaster around them, and from my understanding of paleontology or like traditional digs and things like that. I mean, you're digging up this bone and then you're wrapping it in plaster and all that, but and you might like carry it out, or you might get like a helicopter or a forklift or whatever.
Right.
But here you have to just grab it, put it in a pack, and then take it with you.
Yeah. And there's, in most places that wouldn't work. Most fossils that I've ever collected, I would never put in my backpack as a means of transporting that back to the lab. It's gonna break. Yeah. But in this circumstance, they almost never break. These bones are so strong because there's so much calcite infused into them. Yeah. Right? So that's bad for my ability to get collagen. Forget about ancient DNA. Just forget it. It's not there because of the calcite deposition and the process that led to it. Yeah. But it's great because without that, it would be so difficult to collect these fossils. Every single one would need to be packaged so carefully, and in some cases even in plaster jackets. And so collection would be much slower. We'd be taking out only a few things each time we went, right? It would be really, really cumbersome field work. But things line up and work out. Yeah. There are, in Natural Bridge, I had to make a plaster jacket. So there are circumstances where you can do this, but again, we were in a pit room. So we had to put the plaster jacket in kind of like a pelican box, then attach that to rope, then have somebody pull it up out of the room, right? We still, even though we're using this much more traditional sort of paleontological collection method, we still can't just walk out with it, right? The cave is dictating how we can collect this stuff. Yeah. And there's some stuff that maybe I wouldn't collect, because I don't think we can actually get it out of the cave without crushing it into a bazillion pieces.
What ends up happening to those? You just leave them in place?
Yeah, I think in most circumstances, people ask me all the time if they should bring me fossils when they find them. Mm-hmm. In most circumstances, no. They should stay where they are. They're better off. They've been preserved there for some amount of geologic time. That's probably the better place for them. Yeah. And yeah, if that's if that's the situation that I'm looking at, is I try to take this out and there's a very good chance I destroy it, or I leave it here and it is preserved until some point in the future. Mm-hmm. Yeah, that's easy choice for me. Leave it there.
Take a picture, put it in the discussion section.
Right,
yeah,
right. Yeah. Maybe we use photogrammetry, right?
Yeah.
Maybe we try to get a scanner or something in there and document it in a different way, mm-hmm. rather than trying to obtain the actual thing.
Well, I think we've kept you long enough. thank you so much for meeting with
man,
me.
it's my pleasure.
Yeah, this has been a super fun conversation.
Yeah.
And all the cave stuff, and not even the cave stuff, but the whole science behind it, and I think paleontology in general is very, very cool science. Like it really cool. I remember when I was a little kid, have you ever seen Nigel Marven?
No.
So there's this series called Prehistoric Park, and then it's another one called oh man, how did I forget the name? I watched it like every day as a
Really?
kid. Yeah. But it's basically like this he's a wildlife biologist from Australia or New Zealand. And he had this like BBC or maybe he's British actually. He's got some sort of, he speaks English, but he's got an accent.
Right.
There
Okay.
we go. And I should know this. He was like my childhood hero. Anyways, yeah, I just like would watch that, and I forgot how we even got the DVD to it. I think my dad thought that I would like kind of like it. I think it was cool. And I used to watch it like every day, and I'd always pretend I was Nigel Marven. And I just think the paleontology stuff is so cool. And I think the implications of it, like we were talking about earlier on climate change and these very large questions that can go into other sciences like glaciology,
Right.
or like, I mean, there's this saying where like you're always, I think, like 2 or 3 people removed from everyone else in the world. And I think it's the same thing with science. Like discoveries in paleontology,
That's cool.
like, or like a geologist going out and studying the seashells can tell you about the glaciologic history of this island. Glaciologic history can help you, you know, run your huge supercomputer simulations of mantle dynamics and crustal rebound. And like, and then from that you could like go into crystal fabrics of olivine within the upper mantle and how it changes according to stress. And it is so I think my whole point is that I think it's just really underrated stuff, and it's really, really interesting.
I agree.
Yeah.
I gotta agree.
Yeah. Well, thank you so much, sir. I appreciate it. Yeah.
Yeah.
Cool.